In this one, we're going to talk about a few subjects. The first one being fatigue and wear. Now, fatigue is more of a problem that usually evidences itself by a tooth breaking off. And a lot of times that's just due to high load. So the first thing you can do is get your diameters up. And what that really does is it sometimes eliminates the amount of torque that needs to be produced and lowers your tangential force. All right, the other thing it does is if you go to a bigger number of gears, it actually raises your Lewis form factor. All right, and we're still working under this equation. And the other things we can do are we can raise our allowable stress, and that could be done just by using a stronger material or possibly hardening that material. There is a cutoff as to how much that will help you in fatigue. Obviously, if you're getting up to 180, 200 KSI on your gear teeth, may want to change and try a different design. We can increase our rack width, or just our gear width, sorry, or we could decrease our pitch diameter. And with all these things, there are trade-offs with power transmission and just the size to put all these things in. And maybe you find that gears just aren't the right method of transmitting that power. Maybe something, a V-belt or a chain and sprocket system would be better. Who knows? So one thing you can do with gears to make sure they don't have premature wear is to make sure that they don't mesh with the same teeth every time they go through. All right, so if we look at this, this gear has 24 teeth and this one has 40 teeth. All right, I can divide both by 8, so this would be 3 and 5. So for every 5 revolutions, it's going to line up perfectly again with the teeth on this one, which will have completed 3 revolutions. And that's not terrible. But if I had, let's just say this was 24 and 48, that means every 2 revolutions I'm hitting on the same teeth. And that's, that's getting down there. But if I had 23 and 48, wow, that's quite a few revolutions away that they'll mesh again. And that just helps us to keep the pinion teeth wearing, because generally speaking, the smaller gear is going to wear faster than the bigger gear will. All right, so we want to make sure that we look into that when we're designing our system and just see, can I just make this of a weird number of teeth. The second thing I want to talk about is material. All right, so your materials are an important thing. You basically have 3 categories. You got plastics, you've got brass and its subsidiaries, and then you've got steel. And you'll see gears made out of different things, but we'll just kind of go through them and highlight the good and bad things of them. We won't get very deep into this. There's a lot of research that can be done here. So plastics, these are more for precision, low torque things. Lego gears are made of plastic because they can withstand high speeds fairly well. They don't shave on each other much, and basically they're going to last as long as you're not transmitting a lot of power. All right, as you get down to the harder materials, brass, probably the first chance that you're going to actually be able to transmit some sort of power. The wear is pretty good on that, but as with metal on metal, you're going to have more heat building up, so you're going to need something to remove that heat. Lubrication is a great way to, 1, prevent the heat from starting, and 2, just remove the heat immediately. It'll flow right into the fluid and be okay. And then steel, you can get that really hard. You can transfer a lot of force through gears, and that's probably the #1 choice of bigger gears is steel. Obviously, they cost more than plastic gears, but they'll last a lot longer under the loads consuming. One of the things that I haven't touched on is with these is speed. Plastic gear, plastic is much lighter than steel, probably about 1/4 to 1/8 of the weight. So you're not going to have a bunch of mass trying to fling itself. You don't have to worry about out of balance as much. So if you're using it high speed, plastic is going to be a much better material than steel will. All right, well that's all I wanted to focus on materials. So the last thing I want to talk about in this video is runout. Runout is the eccentricity of the gear to the shaft. So there's 3 different kinds. There's axial, angular, and radial. All right, so radial is very simply put, I have a shaft and then I have a clear, distance that it is out of round. All right, and that's shown right here. As it goes around, it's gonna flop around like that. That's radial runout. Axial runout is if I have a gear on a shaft and I put an indicator right on the surface and I watch the dial as I go around. What is it moving? And probably have a tolerance of what is acceptable. If you're doing it on a large crane rotation bearing, 1/4 inch may not hurt you. But if you're doing something precise like a clock or a watch or something like that, 10,000ths may be way too much. And then angularity. This would be, how the gear is pressed on the shaft. You want to find out essentially what is this angle right here, and that's going to tell you something. That kind of is tied closely with the angular or the axial runout. So just so you're aware of those things and you can keep an eye on them. Now there's 2 types of gears. There's normal gears that you'll buy, and then you can buy precision gears. And these things, somebody's spent the time and you will spend the money if you use them to get these, where all these runouts are very small. The teeth are almost exactly identical. They've probably even been put on a CMM machine, a coordinate measuring machine. Well, they will go through and trace the profiles at various depths through the gear tooth. It's there, you can buy it, and it's expensive, but these things will be minimized. However, for a lot of cases, probably just don't need it. The last thing we want to talk about here is backlash. Backlash is something that all gears have, and we want to try to minimize it in certain conditions. It's basically a sloppiness between the 2 gears. So we run a balance between the 2 gears, meshing on this side and having a gap over here. You can see this gap right here. If we have like a crane pivot where it's rotating side to side, we probably want to keep that fairly tight because we don't want the crane going jerk, 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 and then it's got some momentum every time it hits each side of the teeth. It's going to wear. It might even fatigue a tooth off if we were to do that, several hundred times. So you want to get that fairly tight just so it feels snug. And as I mentioned earlier, you basically want to go in and be able to adjust that dimension. My favorite way to adjust these is to take one of them, usually the pinion, and make an eccentric hole for it. So I'd have my hole directly on top of that, and then I'd have another hole. Now pretend those are round, I'm sorry. My freehand drawing is not that good. But you can clearly see that, let's just say, the center of this hole, the inner hole, is there, and the center of the outer hole is there. And maybe, I don't know, depending on your application, that's 1/16 to 1/8 of an inch off center. Whoops, 1/8, not 18th. And you can adjust that as needed by rotating this around, and they go closer together or further apart. Now what you'll need is some way to lock them in place. There's some way to do that. You can kind of put almost teeth on this and then have some sort of plate lock that in, or something like that. You'll have to get a little creative there. I've got some ideas, but they're proprietary, so I'm not going to share those. So that's just one way to do it. You can just clamp them together, clamp this to something else, and just allow friction to account for that. That might loosen up over time. You probably want more of a positive engagement. So the way you would measure that is you would take whichever gear remains steady. Let's just say it's this one. This is the pinion gear that's driving this gear. What we want to do is get in as close as we can, and we're going to mount a dial gauge here. Oops, so that's not a good. So what we want to do is we want to come up on this tooth and get as perpendicular as we can and put a dial gauge here and have it mounted back to this gear, whatever holds this gear, that whole mechanism. And then we want to just rotate it back and forth until we get whatever amount of backlash we're okay with. But it basically just measures how much change is going to happen when we rock this thing back and forth. Generally, you want to see 5 to 10 thousandths or something of that nature. If you get tighter than that, you're going to start to bind this up right here. Also, a lot of gear manufacturers know that their gears aren't perfect, and they will actually indicate to you, usually by painting on there, which teeth are the highest or the most oversized, the target. So that way you can mesh those ones and then put your dial indicator on that and do that. So if you don't know which ones are the high ones, you may have to do this several times. Okay, well, thank you for watching this episode. Be sure to join us on the next one.